picking up good vibrations.
The Dirac is also called an impulse or a delta Dirac, or just simply the delta function. In this discrete time, it is very easy to define it. It's simply equal to 1 when n equals 0 and 0 for other values of n. However, in continuous time is a very delicate function to define. It's actually not a function, it is a generalized function. It is obtained as the limit of a family of functions. How do we define this family of functions? Very easy. We define a function which is a rectangle that is 0 outside the interval from 0 to capital delta, and we multiply this rectangle by 1 over delta. So it is equal to 1 over delta in the interval from 0 to capital delta, and it's 0 outside. It's a family of functions parameterized by the parameter capital delta. As we make delta smaller and smaller, this function becomes thinner and thinner and taller and taller. In the limit as delta goes to 0, we can intuitively say that it will converge to infinity when time is 0, and will be 0 for any time t except t equals 0. So informally, we can write it in this symbolic notation where we put an arrow indicated as infinity when n equals 0, when t equals 0, and it's 0 otherwise. Now, we are going to use this definition in this course, but I want to mention that in many textbooks it's common to use a very similar definition where this family of functions goes, instead from 0 to capital delta, goes from minus delta over 2 until capital delta over 2. It's not a problem. Our definition will fit our purposes. Now, there's a very important and crucial property of the delta Dirac, is that if we place a delta Dirac inside an interval, let's say that we have the interval from minus infinity to infinity of an arbitrary function gt, which is bounded and continuous, times delta of t minus tau. This interval will be equal to g evaluated at tau. Intuitively, it's very easy to understand this. This Dirac delta of t minus tau is now centered around time tau. So we have a function, once we multiply by the Dirac, it's going to be 0 everywhere except when t equals tau. So just around this time, when t equals tau, this function is going to be non-zero. If I take the interval of g times one of these limiting functions, which are rectangular functions in the interval from tau until tau plus delta, the area is going to be 1, but they are multiplied by some values which, as delta goes to 0, are very, very similar to g of tau. Since a function is continuous, as we make tau smaller and smaller, this interval will become closer and closer to g tau. Now, Diracs are very convenient, and in particular, we can write any function as a weighted sum of Diracs. In discrete time, this is very, very easy to see. Through this example, we can understand that the function that is plotted can be written as 2 times a Dirac centered at 2, so delta of n minus 2, plus 1 times delta of xn minus 3, so a Dirac centered at 3, plus 2 times a Dirac centered at 4, delta of n minus 4. And in general, even if the function is not 0 outside of bounded interval, we can always write it as the summation from L equals minus infinity to infinity of the value of x at L times a Dirac centered at L, which is basically delta of L n minus L. In continuous time, this follows from the property that I just mentioned. We can always write a signal x of t as the interval from minus infinity to infinity of x of s delta s minus t.